Okay, so we're working on linear inequalities today. So what we're combining here, if you think back to what we've already done, is linear, which hopefully in your mind rings line. And we're also going to combine inequalities, which remember were these kinds of things, or we had something like, I don't know, x is greater than 3, and we would have to graph that on a number line, kind of like this, where we'd have our 3, we'd have an open dot, and then we would shade in one direction or another. So what we're going to do today is we're going to wrap these, like with our y equals mx plus b slope, all that fun stuff, with these. So we're taking two things you already know and mixing them to make something new. So what you're going to see is equations that look kind of like y equals mx plus b, but this time they're going to be inequalities. So instead of an equal sign, you're either going to see one of those 4 inequality symbols that we had from Unit 1. Your graph is going to look like a nice straight line. But this time we're going to have some shading. So that's part of where our straight line is coming from the linear part, and the shading is coming from the inequality part. Now the symbol is going to give you all the information just like it did back in Unit 1. It's going to tell us what kind of line we have and also where to shade on our graph. So if you think back to Unit 1, both of these symbols were an open dot. Okay, both of these symbols over here were a closed dot. All right, so it's going to be kind of similar. You can't really show an open dot on a line here, but what we're going to do with our line instead is we're going to make it a dotted line. So if you want to connect dotted line to open dot in your mind, that would be a really good idea. Okay, over here, if you have a closed dot, it's going to be a regular, normal, solid line. One way to remember that is if you see a solid line underneath of your symbol, then that means you have a solid line. The shading is what people tend to have trouble with. So what this means is if you have something that is less than, like either of these two symbols, you're going to end up shading below the line that you have. One way to remember that is less than, you want to think small or low, so you can connect that to below in your mind. What that will look like on your graph is if you have a dotted line, kind of like this, it's positive, you're going to end up shading on your graph below that line. It looks a little bit different if it's negative. I'm going to draw a solid line there. The below ends up being on a different side. All right, similar for this guy over here, just we'll have solid lines. So if it's positive, below will be here. If it's negative, below will be here. All right, on the greater thans, we're going to shade above our line. So you're going to see similar things again. If you see something like this, we would have a dotted line. Above would be on this side. If your line is negative or decreasing, it's going to be on this side. All right, similar deal over here. Above is here. If it's positive, and on more to the right if it's negative. All right, so we're going to use those things to now graph inequalities. All right, we're still going to use our whole slope-intercept form, the whole y equals mx plus b idea, keeping in mind that this guy here is your y-intercept, which will be on the y-axis. This guy's our slope. And we're going to treat that like rise over run to get from one dot to the next. So we start like we normally would. See how it kind of looks like y equals mx plus b? That's great. So we're going to start here. That guy's b. And that's going to go on the y-axis there, positive 3. All right, from there we're going to use slope like rise over run. I need a run, so I'm going to put that 2 over 1. So from that dot, I'm going up 2 spaces and over 1 space. Okay, I am going to extend my line all the way across the graph. So remember, you can use your slope backwards, going -2 and -1, and that will still maintain that positive slope. Okay, this is where you want to pause for a second. It's not quite like graphing a plane line, because now I have to make a decision based on my symbol. So my symbol is a less than symbol, meaning that my line is going to be a dotted line. So instead of connecting all of my dots with a nice solid line like I usually would, we're going to make that a nice dotted line. All right, there's one more step, and that's to decide on shading. So again, sticking with that same symbol, I'm going to need to shade below this line. Since I have a positive slope, I want a shading that looks kind of like this. So we're going to be shading this side of our graph. This is a great section that if you have crayons or colored pencils, highlighters, anything that can help color, it works really, really well. Kind of like that. All right, now the graph represents your solutions. So anything here in this colored section, this represents solutions to that inequality. So if I grab any coordinate out of that colored area, it is going to make this inequality true. Anything out of this non-colored section would be false. All right, we'll talk more about that in the bottom section of these notes. All right, here's another example. Okay, we're starting at B, here at -1. Slope says to go down 1 and over 3. So down 1, over 3 to the right. We only use that negative on the slope one time. I can use it either on the bottom or on the top. Kind of like this. All right, if I check my sign again, this is again where we pause. Looks like I have a solid line underneath. We have this symbol here, so we are working on a nice straight line. Nice and solid. There we go. All right, again, we're going to end up shading above here because of my symbol. Okay, and because my slope is negative, above is going to be up here on this side. All right, looking good. Now, where it gets a little bit funky is if your inequality does not look like y equals mx plus b first. That means just like before when we were trying to graph and it wasn't in the format that we needed, we do need to get y alone. So I'm going to move the x to the other side using subtraction. We'll put that x first just to make sure that it looks more like the mx plus b part that I'm looking for. And my final step here is going to be to divide by 2. Now, because we are dealing with inequalities, if I had multiplied or divided by a negative number, I would still need to flip the sign. That rule does come back into play. All right, once y is alone, this is the inequality that I'm actually going to end up graphing. All right, so we'll start here at +3, just like on our other examples. Slope says to go down 1 over 2. So down 1 over 2. And I'm going to keep that pattern going. I'm also going to use it backwards, so +1 and then -2 to the left. All right, I check my symbol. Make sure you use your rewritten symbol in case you had flipped. Don't go back to the original. But in this case, they happen to be the same. So here, looks like we're going to end up with a dotted line. And I'm also going to be shading above. You can also use Desmos to graph these. If you go to Desmos and type these in just the way that you see them, it can help confirm your answers or help you see solutions a little more clearly in case you're having some trouble. Okay, the other kind of question they can ask with this is determining whether ordered pairs are solutions or not. So the thing to know about these inequalities is that solutions are in the shaded area and on solid lines. So again, everything in the colored area over here is a solution, and anything on a solid line also works. It's kind of like your open and closed dots. So remember, things on an open dot or the dotted line are not going to work. That's because it acts just more like a boundary. It's not so much an actual solution. If you plug them in, you'll get something like 6 is less than 6. But even though the numbers match, the inequality is not true. Using the graph to help is really, really convenient. So for example, if I'm trying to determine which of these coordinates are solutions, I'm going to start with the point 1, 1. If I go to where that coordinate is, 1, 1, right about here, all I have to decide is whether that point falls in the shaded area or on a solid line. In this case, it does. So that makes 1, 1 a solution to this inequality. All right, if I check the next one, -3, +1, 2, 3, 4. Okay, also falls in the shaded area, so it is also a solution. if I go to 2 and then -6 all the way down here on the bottom, you'll notice that that one is not in that shaded area. So that makes that one not a solution. If I go to -5, -1, again, no color, no solution. All right, if I'm at -2, +1, this one is one that tends to trip people up. It does fall on the line, which makes it tempting to call it a solution, but because that line is dotted, this does not count as a solution. All right, the strategic hole punch here punched out a number. That number is going to be 4. So really we're looking at the coordinate for -2. All right, so if I'm at +4, -2, 4, -2 is indeed a solution. And last but not least, we have 0, 0, which is our origin, which again falls in that double shade or in the shaded area. So that one's a solution. Okay, we have one more example like this for you. Again, I'll check 1, 1. Looking for coordinates in the shaded area. So 1, 1 is a solution to this inequality as well. If I go to -3, 4, it does not work, not in the shaded area. Right? 2, -6 works really well this time, very clearly in that shaded area. If I go to -5, -1, okay, not in the shaded area, so not a solution. 4, 5 brings us to one of those special points that falls right on that boundary line. Now, because our line is solid, this one does get counted as a solution. Okay, same thing with 0, 1. Also falling right on that boundary line, and because the boundary is a solid line, it works as a solution. Okay, 0, 0 also falls in that shaded area, which makes it a solution as well.